Hello. In this lecture, we will be seeing how to arrive at the orthogonality relation satisfied by Hermite polynomials. For that, consider Hermite differential equation, which is as shown here. From this, we can write P naught is equal to 1 and P1 is equal to minus 2x, where P naught and P1 are the coefficients of y double dash and y dash respectively. It is very clear that P naught prime is not equal to P1. For a differential equation to be Sturm-Liouville type, P naught prime should be equal to P1. But here it is not so. So, Hermite differential equation is not of the Sturm-Liouville type. Now, how do we convert any differential equation to the Sturm-Liouville type? We multiply the equation throughout with a weight factor. And in the case of Hermite differential equation, this weight factor turns out to be e raised to minus x square. Evaluation of the same has been demonstrated here. So, now you multiply your Hermite differential equation with the weight factor, and this is what you get. Now here you can see for yourself that P naught prime is equal to P1. So now we have converted Hermite differential equation to a Sturm-Liouville type problem. Now it is possible to evaluate the orthogonality relation. Now, this is the orthogonality relation satisfied by Hermite polynomials. Here, Hn of x and Hm of x are solutions to Hermite differential equation, and this is the orthogonality relation. Here you can see a delta Nm, which is nothing but our Kronecker delta function. Now, how do we prove this? For that, start with the generating function for Hermite polynomials. Let this be the generating function for Hn of x and this one be the generating function for Hm of x. Now I multiply both relations and this is what I get on my LHS and this would be my RHS. I have not done anything else. I have just multiplied both the relations that we just saw before. Now, what am I trying to understand from this relation? I say that this exponential term is generating a series such that the coefficient of t raised to n, s raised to m in the expansion is this thing. Okay, so if this is the coefficient of t raised to n, s raised to m in the expansion of this exponential, the coefficient of this term would be, see, I've done nothing else. I've multiplied this with an e raised to minus x square factor. On the RHS also, that change would be reflected. This would get multiplied by an e raised to minus x square factor. Now, why did I multiply with this term? If you just recall the orthogonality relation, you have something like e raised to minus x square multiplied with Hn of x, Hm of x. In order to get such a thing, we have initiated such a step here. Okay, now you integrate on both sides from minus infinity to infinity. And why these limits? That we have seen in the previous video. For Hermite polynomials, the limit of integration is from minus infinity to infinity. It will be different for different polynomials. And this is the term on my LHS and this one would be my RHS. Now focusing on the LHS alone. You can take constant terms outside the integration, as this is an integration with respect to the variable x. And now, in order to convert the power of the exponential within the integral to a perfect square, I would have to multiply with this factor. Okay, and the term within the integral, the exponential term, will now have a perfect square as its power, and outside the integration I have such a term after cancellation of several terms here. And now the next step would be I substitute x minus t plus s as u, and my integral would get transformed like this. And this is a standard integral whose value evaluates to root pi. So what do I have on my LHS? I have done all these steps and I have arrived at a point root pi times e raised to 2ts, whose expansion we know, and that is what we have written here. So if you now just have a close look at the terms involved in the square bracket, you have ts in the first term, you have t square s square in the second term, you have t cube s cube in the third term. So every term involves t and s with the same powers. Okay. And now this was the term that I had on my RHS. And on my RHS I have a term t raised to n s raised to m. Okay. So now if I equate the coefficient of t raised to n s raised to m on both sides, specifically with the case n not equal to m. Now if you look at this series, there is no such term where the power of t and power of s differs. So the coefficient of t raised to n s raised to m would be 0 from this side. So equating the coefficient of t raised to n s raised to m under the condition n not equal to m on both sides would yield such an equation. Am I clear? Equating the coefficient of t raised to n s raised to m on both sides. On this side I would have this integration, but on the right side I don't have such a term, so it will be 0. So that condition yields such an integral, and this equation I number it as equation 1. And another condition, n equal to m. When n equal to m, I do have a term coming in from my RHS2, and when I equate the coefficient of t raised to n s raised to n on both sides, this is what I get, and from here I get equation 2. Just transporting this n factorial to the RHS, I get equation 2. Now I can combine equation 1 as well as equation 2 in a single relation by using Kronecker delta, and my relation would be like this: integral minus infinity to infinity e raised to minus x square hn of x hm of x dx is 2 raised to n root pi n factorial delta nm. Now here I've used the specific property of delta nm, whose value is 0 when n not equal to m, and when n not equal to m, I get my equation 1 from here, and when n equal to m, I get my equation 2 from here. So the two relations, equation 1 and 2, can be combined in a single integral with the help of Kronecker delta, and this is the orthogonality relation that I require and that is satisfied by Hermite polynomials. I hope you have understood what I mentioned in this lecture. Thank you for your patient listening.